Let us move on to our next topic, addition of halogens to alkenes. As we all know, the addition to an alkene is a very simple process, but it has a lot of stereochemistry involved in it. There is no regiochemical issue in the addition of an halogen like bromine or chlorine to an alkene because the electrophile and the nucleophile are both the same. But the question of stereo selection is more significant here. Whereas in the addition of HX, a hydrogen halide to an alkene, the addition of electrophile leads to the building up of positive charge on the adjacent carbon, eventually giving rise to a planar carbon. In this example, when we try to add bromine molecule to carbon double bond carbon, the first step is the formation of a cyclic bromonium ion. Therefore, the nucleophile attacks the other carbon in an Sn2 fashion, giving rise to an anti-addition product. Subsequent reaction with the nucleophile can in principle take place on either face of this cation, which produces a mixture of Syn and Anti Addition products in the case of addition of HX to an alkene. In contrast, the bromination of alkene is stereospecific. It is anti-selective due to the formation of a intermediate, which is a cyclic bromonium ion. The overall process is anti-addition of bromine to the double bond because the cyclic bromonium ion undergoes ring opening in an Sn2 fashion, that is strictly by inversion, in which the Br minus counter ion serves as the nucleophile. This Sn2 step takes place at the most electropositive carbon of the cyclic ion, that is where the location of original positive charge. The attacking nucleophile can also be a solvent, and the resulting combination of versatility and stereospecificity makes the reaction very useful in synthesis. When the cationic center is strongly stabilized by structural feature, now in this case we have a molecule where the carbocation that is formed can be stabilized by resonance. The non-selective mechanism via free carbocation always competes with the bridged ion pathway. Therefore, in this particular reaction, there is a possibility for the formation of a cyclic bromonium ion and also for the formation of a free carbocation, and therefore the reaction ends up with 88% anti-addition and 12% Syn addition, which is formed by carbocation pathway. Let us take another example, which we call it as hydroboration of alkenes. Hydroboration is a very important synthetic process. Borane is electron deficient and it readily reacts with pi bond, which is electron rich. The addition is highly regioselective because the boron atom adds to the least substituted end of the double bond. The addition is stereospecific in nature too, with the boron and hydrogen atoms always adding to the same face of the double bond, and we end up with a Syn addition. The reaction is stereospecific because the Syn addition takes place via concerted mechanism, and the reaction is regioselective because the boron adds to the least substituted end of the alkene, and the reason for the entire process is due to the concerted bonding mechanism, which gives you an exclusively Syn addition product. Let's look into another type of reaction called elimination reaction. Now, in an E2 reaction, the base tries to remove beta hydrogen and forms a double bond and kicks out the leaving group. The reaction occurs through a concerted mechanism and requires a beta hydrogen. This elimination is also known as beta elimination reaction. As in the SN2 mechanism, the mechanism of transition state formation can be deduced using a stereocenter. There are two possible modes of reactivity that yields two different stereoisomers. In Syn elimination, the base attacks the beta hydrogen from the same side as the leaving group. Whereas in an anti-elimination, the base attacks the beta hydrogen on the opposite side of the leaving group. Now, what is the outcome? It has been experimentally determined that E2 elimination occurs predominantly through anti-mechanism. Now, why does this happens? When we see an SN2 reaction, the mechanism shows us that the reaction occurs through a backside attack, and we have a lot of steric and molecular orbital explanations for the E2 anti-elimination process. The steric argument notes that the Syn transition state is an eclipsed conformation and the anti-state is in more energetically stable staggered conformation. Since the rate of the reaction is inversely proportional to the stability of the transition state, the anti-route should be much more favorable. So we can see here that the base abstracts the hydrogen and the leaving group is anti to the hydrogen, which is considered as the most energetically stable staggered conformation, and the sigma CH bond and sigma star C leaving group anti-bond are anti-periplanar. The E2 molecular orbital argument hinges us on the sigma star carbon leaving group antibond, just like the SN2 molecular orbital argument. In this case, the sigma star carbon leaving group antibond is only accessible to the electrons of the sigma CH bond only if the two bonds are anti-periplanar, that leads to the formation of a overlapping and ending up with the formation of a double bond. In other words, the carbon hydrogen and carbon leaving group bonds must point opposite directions in parallel planes. If this condition is met, the electrons of the sigma CH bond is donated into the sigma star of the carbon leaving group antibond, which is considered as the most energetically favorable process. In the Syn elimination, the bonds are not anti-periplanar and the electrons of the sigma CH bond cannot attack the sigma star orbital of the carbon leaving group antibond. Thus, E2 cannot occur through Syn elimination. Seid's rule helps us to predict the formation of the major product. Let us take this example. Now, in this particular example, there are three hydrogens, beta hydrogens, but only two of these hydrogen may be anti-periplanar to the carbon OTS at one time. Now, how can the two hydrogens of carbon B give two products, even though only one can be anti-periplanar? This is quite interesting. While only one hydrogen of carbon B can be anti-periplanar at a time, one need to understand that both these hydrogens can spend some time in the anti-periplanar conformation, or in other words, the possibility of this carbon to undergo rotation enables these two hydrogen to spend some time in anti-periplanar position. Thus, the elimination of the hydrogen of carbon B gives cis and trans product, and this is possible because alkanes that are not inordinately hindered rotate about their carbon-carbon bond, and that is the reason why we end up with three different products. But one need to understand that product 3 is the major product because an E2 elimination favors the formation of the most stable alkene. Now, how do we say that this particular alkene is most stable? The stability of an alkene is proportional to the degree of substitution at its double bonded carbon, or in other words, the most alkylated alkene is the most stable alkene, and that is preferred in any elimination reaction, and that is what we call it as Zaitsev rule. The double bonds of products 1 and 2 are less branched than the double bonds of product 1. Thus, there will be more of product 3 than products 1 and 2 after the reaction has run to completion. Elimination reaction preference for the more stable alkene is called Zaitsev rule. So what is Zaitsev rule? According to Zaitsev rule, a more highly branched alkene is formed, and even in that formation, the trans product is most favored, and the product is formed following all the anti-periplanar conformation rule. Thank you for watching.